I did Advent of Code for the first time last year, and I used a language called Janet. It was a lot of fun, and I wanted to go through some of my solutions to the problems as a way to just kind of demonstrate what the Janet language actually looks like in practice. And I think it's a really good fit for problems like this because it's really, really good at manipulating text. So all of the kind of parsing beginning of the problem where you're given some big input and you have to turn it into an actual, like make sense of it so that you can solve the problem itself. Janet sort of makes that part really fun and really easy. And it does this through this feature called parsing expression grammars, which are sort of Janet's equivalent of regular expressions in other languages, except that parsing expression grammars are a lot more powerful, composable, easy to, well, we'll take a look. We'll see. So let's just dive into the first problem. And I'm using Judge, which is a test framework that I'm going to use as just my way that I interactively write Janet programs, as rather than the traditional like connect or REPL and evaluate expressions that you might see in some actual Lisp users' workflows. I am an OCaml user, and this is my workflow, so we're gonna see it here. So we have this Advent of Code day one problem, and I've already copied the input. I've already solved the whole problem, so I already have part two. But essentially, we're parsing these lines. We're taking the first and the last digit on the line, treating that like a two-digit number, and then summing up all of the two-digit numbers from the line. So this is 77. So I'm gonna do this with a peg. So I'm not gonna explain in too much detail like the syntax that you're seeing here. I think it's better to just kind of pick it up as you go. But I'm going to write a peg, and the entry point is always called main. So I'm going to split the input on new lines, and then I'm going to parse a line. And I'll make another sub-expression here for what a line is. And a line is one or more of either a single-digit number or any other character. So one in a peg means like advance one character capturing nothing, kind of like a dot in a regular expression. And number colon D, this is like backslash D in a regex, and this means parse a single digit character and then convert it into a Janet number, which is like a JavaScript number, it's just a 64-bit float. Uh, and what this is going to do, if I demonstrate using peg match, so let's just match it on the test input, and you can see my like judge workflow in action here. Uh, so that wasn't probably what we want because when we did this split, there's something correlating the line itself. So it parsed all the numbers, but it didn't remember which one belonged to which line. And we can fix that by just adding a group here. So it's going to say, take all the captures, match this subpeg line, and then take all the captures and group them into an array at the end. If we run that again, we can see, yes, now each line is actually grouped. And then from there, what we can do, I'm just going to make a function for it. So given input, I'm going to parse the input. And then I'm going to use seek, which is Janet's list comprehension, basically. And it uses this kind of funky DSL, which I won't try to explain. I think it's pretty natural, but there's lots of documentation and explanations of it. So seek line in the parse input, and then we'll take the first and the last from the line. We will sum them, and we will multiply this one by 10 so that we get the two-digit number. And then I will test solving the test input, see how that did. And 1, 2, that looks right. So we turned each line into a two-digit number, but that's not actually what the problem wants. The problem wants us to take the sum of all of these numbers. So Janet already has a sum function, 142. And let's go to the Advent of Code 142. Okay, so you got it right. And let's try the same thing on the real input. And oh, something's wrong. Oh, whoops. Solved this in the wrong spot. Okay, 54951. So I already solved it, but that is right. And then we move on to part two. And part two is a lot more interesting. I think pegs really have a chance to shine here. So I'm just going to copy what we did so far and modify it for part two, which we could use the same code for part one and two, but we extend this by having number words that we had to parse. So this is the same as the input 219. And the trick here is lines like this, 823, where this is the same as 823, even though you could sort of naively do this wrong and parse it as 8 and then just have the WO left over and then 3. So we're going to make sure that we handle that. So a line is still, instead of saying a single digit number, we're going to say it is a number or skip to the next character. And I'll say that now I'm going to define a number as either, we can still parse single digit numbers, or it is the string like 1, for example. But when we parse the string 1, that's not going to capture anything. So we have to use this. So this says parse this first expression, and if it succeeds, capture the second expression. Uh, so I'll just try out like a very simple version of this. So I'll say 1, 2, 3, and get rid of, well, all the rest of it's basically gonna be the same, but so that works already. We parse the 1 and we capture this, but if you do this for every single, this is boring, but 3, 4, 5, 6, 7, 8, and 9. And then we're just gonna capture the right values. You'll notice that this doesn't actually work. So I'm going to try 1, 8. And that only captures 1 because it doesn't realize that. And that's because when we capture this 1, we're also going to advance over all of the input. But we can change that. We can say, if you capture this 1, then only advance a single character. And you can put whatever expression peg. This is just another subpeg. Say if this one succeeds, then run this one. And this one just says skip over exactly 1 character instead of skipping over all of the input that you parsed. And that already fixes it for 1, but of course we want to do this for all of them. So we'll wrap this all in another choice. And we'll say if any of these match, then advance by a single character. And still works. And then our solve function is otherwise identical. So just test that. So 281, and that matches the example. You can also just take off the sum for a second to see yeah, we get the 83 from 823. Oh, well, this one, I guess, it still succeeds whether you do it correctly or not, but yeah, we have our own test case for that. So take the sum and do it on the whole thing, 55218. Still works. Okay, so we're done. That was day 1. And there's a lot that we could change about this. Like, we don't have to put these all in one group. You could say, like, if you match this, then actually you can advance 2 characters because the only like suffix here that is the prefix of another number is the E. So you could advance 2 characters, and you don't actually have to do it at all for 2 because no number starts with an O. 3, you can advance over all of these other characters and just make sure you leave room for the 8, but whatever, we don't care about that. We're gonna not really worry about performance very much. These are how I solved the problem originally, and there's much more efficient ways to do all of these. You can reverse the input, and then you don't have to think about like double parsing if you parse the reverse numeral and all kinds of like clever tricks. Uh, but I do want to talk a little bit about this. This is just day one, but having done all of them, I know that this is a pattern that comes up all the time. This parse a bunch of things and then take the sum of them. So this like sum over seek. We do this a lot. We do this so much that I ended up writing a helper for it. And I thought it might be kind of fun to talk about what that looks like because it's not a helper function. And I'm using seek and I'll, I'll, I like this DSL for doing list comprehensions, but you could also do this using map. So this is sort of the more functional maybe version of this, which I'll write as map, and then the function comes first, which I do not love, but we could do this with a uh, Janet has this short syntax for declaring functions where the argument is available as this special dollar sign. So we could say map all of these and take the sum of that and then rerun, and we can see that all our tests still pass, so we didn't break it. Um, this is kind of like the functional way to write this, and it's easier to write a helper function that is like both sum and map, but I don't really like this. I mean, this is like fold essentially, right? But because of this like argument order problem, I find myself reaching for seek a lot more, especially when like this gets to be multiple lines, becomes a longer expression. So instead of writing this as like reduce plus from 0, and then, oh gosh, it's not even that, is it? It's like map and then reduce it. So I'm just going to write a helper to sort of use this same DSL that seek and loop use, but to write it as a fold. And I'm going to do that as a macro because these are all macros, and it's kind of just a fun way to talk about macros. So I'll call this fold loop, and it'll look like this. We'll write the sum seek thing, but sum is really just a generalization, a specific example of the general operation of folding over a list of things and collecting the results. So we'll write something like fold loop 0 plus, and then we'll give it like the lines here. This is how we're going to use this. This is our little uh, list comprehension language, and then the body is going to be exactly the same. So we'll write something like this instead. And the reason that I want to do this is not just because it comes up a lot, but because seek is actually instantiating an array of all of these elements. And there's not that many elements, and it doesn't really matter right now, but this is allocating memory for each of these and then iterating over it all and summing it again. And there's sort of like a more imperative and efficient way to do this, which is like var total is 0, and then we just say loop over it and say total, add to that and then return the total. Still works. But we don't really want to write code like this in our own like application logic. We would just want to abstract all of this kind of messy imperative mutated local state into helper functions that we can then just call. So I'm going to make this helper function for fold loop, and it's going to expand to be exactly the same code, but we can do it for an arbitrary operation. We only have to write it once. So we will take the initial value, we'll take the function that we're folding with, and then we'll take, I'll just call it the DSL. It's like the loop expression that it's used to, and then the body. So this is going to be, it's going to return an abstract syntax tree that says do var result starts out as init. And we unquote that to get it into the result. And then we're just going to say loop using the DSL and set result to f of result And we want to take all of the body expressions and turn them into a single expression. So we wrap it in do, and we use unquote splice so that you can put multiple expressions. This is like, think of this as like dot 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 in other languages, or in Python, this would be like star body, I think. This is like all the remaining arguments, and then we'll splice all the remaining arguments into a do to turn them into a single expression, call this, and we have this. So let's just test this with full loop 0. Ooh, I forgot to unquote f. That's going to be a problem. So, and I'll just give it 1, 2, 3. And I want to test this. And it did not work. It did not like that at all. Expected loop verb 2. What did I do wrong? Loop the DSL, set result to f of result do body. Well, I'm not sure exactly, so I'm going to use Judge's built-in test macro to see what I've actually written here. Uh, yes, I just passed it the wrong arguments. So this would be like x, I've forgotten how this works. I'm not writing a fold, I'm writing this DSL, so x in 1, 2, 3, I'll give it x. So that actually looks right to me, and it looks like if I test the same expression, just copy this, not test macro, I get a cool nil because I forgot to return. So now we'll return result. Okay, and now I get 6, which is what I expected. So this is a terrible, terrible macro. This is like an example of exactly how you do not write macros. So that's why I wanted to talk about it, because macros are kind of tricky to write, and there's a lot of different mistakes you can make, and I've made all of them in this example. So let's actually try to make this better. And if we look at the macro expansion, you can kind of see why, which is that we introduce this result variable. And this is like a literal actual variable. So if our own expression, here I just put x, but you could imagine that we had like a local variable result. And I wanted to say like plus x result. And now, if I test this, now I've like shadowed this result in here. So to get around this, we're gonna use gensym. And gensym is gonna just return every time a sort of random symbol. It's not clearly random, but it's going to return a unique symbol. And we'll use this to, instead of making a variable called result, we'll make a variable called some generated symbol name. So there's really helpful with sims. And just by convention, these generated symbols, I prefix them with $signs for symbol. This is the result symbol, not result itself. So I'm going to say, instead of result here, and then return it. So great. And now if I look at the expansion, there's no more shadowing problem. We don't have results showing up in multiple places. So this is much better and actually like pretty good. There's sort of a pretty subtle problem now at this point, and it's not something that you'd probably ever actually run into, but since this is just a time to talk about macros, we can talk about it. So it's this plus. So I put an arbitrary expression here, and plus is a constant, easy. It doesn't matter how many times you evaluate this. But I just stuck this expression in here and pretended this instead was like do something expensive and then plus. Well, I would kind of expect, if I just looked at this code, that I only do something expensive once. But actually, the way that I've written this, I'm going to do something expensive every time through the loop, because I just stuck, f isn't the function, f is the code to get the function. And every time we evaluate the loop body, we're going to run the code to get the function. So I actually only want to evaluate it once. So what I'm going to do is add another variable, and I'm going to say let, instead of wrapping it all in a do, let f, so I'm only going to evaluate f once. I'm going to store it in this gemsimmed variable so that I don't have a collision. And then I'm going to use that instead. And now if you see this, yes, I only do something extensive once, store it in the temporary variable called one, and then call it down here. Perfect. And of course, we evaluate the body every time through the loop because that's just what this function is supposed to do. So this is like much better than we had, but it's actually still really subtly wrong. And it's subtly wrong. Wrong is maybe even a strong word, but this is good. But I want to point out like one last potential problem, which is that Janet typically evaluates arguments left to right. So if we had something that was actually like an observable side effect, and we wrote code like this, uh, we might assume that this would print one and then print two and then do its work. But actually, because we like hoisted this, you can see that we actually reordered the arguments and we're evaluating them in our macro expansion in a different order than we supplied them to the macro, which is like no one is gonna actually be tripped up by this, but just to be like super duper airtight macro writers, we can write this as instead binding init first and then referring to it as well. So our macro became like much hairier, but now we restore the order of evaluation of our arguments. We sort of make fold loop look more like a function and behave more like a function with its argument evaluation order, but still write all this. So as far as I know, this is a pretty good macro, and you can kind of keep going forever. Where like let, for example, loop or let, both of them are macros. They're not built-ins. And if you use this function somewhere where you had shadowed loop so that it was no longer a macro and was now like something else, now you're in trouble because you're relying on this loop meaning what you think it means. And we're sort of reaching the point where you shouldn't really care about this. If someone shadows loop and then uses your fold loop macro, like maybe it's actually better for you to use their loop. Like maybe they deliberately were shadowing the loop macro, but there is a way around this, which is as macro, and we're not going to go too deep into that, but uh, you can in Janet write macros that are fully referentially transparent. I think this is a really nice feature of Janet compared to some other macro systems that makes this harder. Janet makes it really easy. You would write it like this, and yeah, this depends on no one shadowing as macro, and if you really were worried about that, you could do the macro expansion out of phase here, but all right, we've talked way too much about macros. We have this fold loop. It's gonna come in handy. It's bedtime. It's gonna come in handy throughout the entire advent of code, but usually it's going to come in handy through a more specific instantiation, which is sum loop. So I'll make sum loop, which I'm just basically going to skip the initial condition and the function, and just say that we'll expand to fold loop of 0 and plus with the DSL and the body. And then this, I might actually write this as macro fold loop so that you could use sum loop even if fold loop were not in scope, but I'm not going to really worry about that much. So let's just make sure that that worked. So sum loop x in 1, 2, 3. Just take the sum of x, or let's have some fun. X squared. Cool. That looks good. I'm going to take these functions and I'm going to keep all their tests because tests are great. And I'm going to move these into a file called, I'll just go ahead and make a util file. And then I will import that. So judge is a library, it doesn't get the dot slash, util is a file, so it gets the path. And this will need to use judge. Let's just make sure. Yep. And yeah. Okay. And let's actually use this. So this will now just be some loop, and you can take that. Great. And yeah, all still works. And this actually can be the same solution for part 1 and 2. And we'll just make sure that all of that works. It did not. I didn't love that because I took my tests for the test input. Oh, and the real input is the same, right? Can't just literally copy it. It almost works. We'll keep it separate. Okay, that is Advent of Code Day 1, plus way more than you wanted to think about writing this trivial helper to add a bunch of numbers, but this will come up repeatedly throughout the coming days, so it's good to write a helper. All right, let's check out day 2.